Okay, so does anyone want to start this off with? So we've got a function. What's dy dx? Say again. 4 times a half is. So we've got 2x to the power of 3. Then we've got
3.
So minus 3x.
That's it.
And that's it, because plus 7 we forget about. Okay. Then we've got the gradient of the tangent to the curve at point P is minus 10. Find the coordinates of point P. Any ideas? How? How do you get there? You have to talk us through it.
Where'd you go? Negative 2, 9.
I don't know. I've not worked it out.
I graphed the gradient function, and I graphed the.
So you did y equals, what was it again? 2x cubed minus 3. Okay, you graphed it. So if I've got that, if I graph that, I get that. Okay?
And I graphed the curve.
Graphed which curve? The original one.
Yeah.
So what would that be? So I'm going to do 0.5. Oh. Now there might be a different way, by the way. So 0.x to the power of 4 minus 1.5 x to the power of 2 plus 7. So we graph that as well.
I made my window a little bit bigger.
So
I made it go down to y and then almost negative.
negative 20.
That's max.
Oh, sorry. Yeah. So negative 20 and what max? Just 10 still?
Yeah.
So yours look like that.
And then I did second calc.
Second calc.
Well, I traced the ability value down to close to negative 10 and the gradient function. And then I did value
So we look for value and
x equals 2.
x equals 2.
I mean minus 2, sorry.
Okay. Value negative 2.
And that was where the gradient was negative 10.
Okay.
And then I got to the other line and got to the coordinate.
Okay, so just in case, is everyone following this or
No.
not?
No.
Okay, so let me talk it through. Maybe it's fine. The method is absolutely fine. So what she's done is graphed both functions. Because what we need to know is, it says this bit is the gradient of the tangent is minus 10. So what we're trying to do is we want to find x when 2x cubed minus 3x equals negative 10. Okay? So what she's done is tried to find on that curve, which is this function here, so she graphed it and tried to find where it's negative 10. Now it's quite nice, easy numbers. So did you say you traced and had a bit of a guess first? Right, there is another way. What I was thinking of doing, because I've got that graph, I did it as well, I put it in. I went to second and graph for table, and then I just went up here, look, and went, well, when it's minus 10, it's minus 2. Okay? So I know that x is minus 2 for that. Alright? Does that make sense how I find that bit? Okay. Now what we have to do to find y, because that is not y actually, that's dy dx, right? To find y we do use x equals minus 2 in the initial one. Y equals, what was it, a quarter x, was it half? A half x to the power of 4 minus 3 over 2 x squared plus 7. So again, how do I do that? I can either just put it in, so y equals a half times negative 2 to the power of 4 minus 3 over 2 minus 2. I just work that out. Or, as Case did, that function goes into your calculator. Alright? I'm actually going to switch off the gradient one now, so that I've just got the other one on my screen. And now I just want when x is negative 2, so if I go to second calc value and put negative 2 in that one, I get y equals 9 out. So there's one way of doing it. There are others. But so I do that and I get when x equals 2, y equals 9. Therefore, point P is negative 2, none. Right. So as I've said before, it's all about you find the gradient function, you do something with the gradient function, you then go back to use the initial function you started with. Right, so that should actually. Any questions on what we've just done now? Wise comments about different ways of doing it, or?
So before you went to table and you usually function.
So the first thing I did was I actually I put the gradient function in. All right. So with the gradient function on there, that's the gradient function. And I want to know when it's minus 10. Now there's a couple of ways to do this. I could actually put a line at minus 10 in and find the intersection, but actually I just want to know what is the x. Now here's the thing. If I do second and table, let's say I'm going up in 1s, 2s, and there is no minus 10. Let's say it's going to be a decimal for x. That means I'm kind of going to have to guess in my table what to set my table at. Now, if that was the case, I wouldn't be able to. I mean, this was a nice, easy one where minus 10 appeared. If it doesn't appear, we have to do something else. Right? If the value you want is not in the table, you have to stick in, like, I will put in another line here and put in minus 10. And what that looks like on the graph is like that. Alright? How do I then find it? Well, it's this intersection point. So I then do second and intersect. And you go, like we've done before, left of it. Oh no, sorry, that was line 1, wasn't it? Line 2, and then guess for an intersect. And it tells you I've got minus 2 as x there, so it does it the same way. But if that was a decimal, that would be the way to do it, because you wouldn't be able to guess. So your tracing method, only really worked because it was a nice whole number. So if it's not going to be a whole number, if it's going to be, because it might even be a decimal to like 2 decimal places or something, you'd have to be able to find that. All right. But after we found the x, that's the first step. We then put that into the initial one, into the x value. So minus 2 goes in, and we find the y value. Okay. All right. Anything else? Any further questions? Right. What we're going to do today, we're going to finish off calculus today. Right. So if you've got your textbooks, please, could you turn to page 5? 594. Well, I think I lent mine to someone last time and I haven't got it back, so... Oh no, there's a spare one up there. I don't know whose that is, but... Maybe that. Probably my other spare one. Okay, so what we're doing is we're looking at the final aspect of calculus that we talked about. We're talking rates of change. Right? And we're looking at the notation and what it means. So far we've done calculus as just finding the gradient. And that's still not changed. We're still using that. So we're starting on page 594. And we are considering... Well, let's go back to our straight lines and let's talk, how do we find the gradient of a straight line?
Rise over run.
Rise over run. Okay, so if I find 2 points and I go across and up, so the rise, we've now got the change in y, right? And then this is the run, which is the change in x. So instead of rise divided by run, we now have change in y and change in x. Alright? Now, what we need to consider now is the fact that actually, if the gradient is steeper, what does that mean? So if I take a second line, and I kind of draw it like that. So yeah, we know the gradient is higher. So we know dy dx is different, it's higher. But what I'm looking at is this bit, the kind of change in y bit, right? Now, I've got quite a long run there. So if I was to take the same equivalent run and just apply it there, what can you say about the change in y for that same run? It's shorter. There's less change, isn't there? So this one, I have a larger change in y for the same change in x. Does that make sense? So the gradient's steep. So if I was walking up a mountain or a hill, the steeper the hill, the further higher I get, the higher the vertical distance I get as I walk along. Yeah? Now what this is called, okay? This is the rate of change of y with respect to x. So this is how quickly, so a rate is how quickly. So rate means so if I have a higher gradient, it means y is changing quicker. The rate of change of y, it's a higher. So all we're doing is we're interpreting things slightly different. It's still gradient, it's still higher gradient, that kind of thing. So the rate of change of y is higher if the gradient is steeper. Right. So, what we need to do, so normally in this particular topic, part of the topic, we have more sort of applied things. Alright? So, just looking over the page, page 595, there's a few things. So we've got function notation. Now, s of t, instead of f of x, s of t, okay? Now this models, so modelling is where you fit a function to some data. So it says in your book, it models the distance, okay, the distance travelled in a given time, okay? So if I said to you, well, we haven't actually got a function, but let's say s equals 3t plus 4, for example. All right? How would you use that? So I would say after 5 seconds, okay, after 5 seconds, okay, we would do the distance travelled. S is used for distance travelled, releasing. The distance travelled would be 3 lots of 5 plus 4. So that would be 19. So it depends what units I've used. Alright? So I might say it's meters. So 19 meters in 5 seconds.
Can you do the different number? I'm getting confused for my notebook which one's fast and which one's
The velocity.
I know, but I don't know which one's fast and which one's fast.
Still 25. Still got 5 there you go. Yeah? So after 7 seconds they've gone 25 meters.
Oh wait, that is an S. Those two on the end.
This is an S,
I
yeah.
wrote that.
S. Alright. So that's what that function would mean. Alright? Now, what we need to consider is what would ds dt mean? But ds dt, or we would also say is
Wait, S is.
s dash of t.
Oh,
Yeah. Yeah.
S is distant. S is distant.
Pardon?
S is distant.
S is distance. Yeah. Right. Now this ds dt would be the rate of change of what? Distance. The rate of change of distance with
Why is distant?
respect to time. I think because distance travelled and distance from a point are two different things. So in science they use S for distance travelled and D for distance from a point. So what is the rate of change of distance with respect to time called? Also known as
Gradient.
nope. It is the gradient of the distance function.
Speed.
Speed. The rate of change of distance. So if your distance is changing over time, that means you are moving, yes? And the more distance you cover in the same time, you are going faster. So the rate of change of distance with respect to time is also known as speed. Now, as it says in the book, that will be, if we start modelling and do it at a particular point, that will be your instantaneous speed. That will be your speed at that point. So do you remember, probably in the past, you may have had a curve. I think we were looking at this the other day. And if you want to know an average speed, remember we took those 2 points and we did, you know, rise over run. Okay, so the change in distance over time, we did distance over time. That would be an average speed. But do you remember how we then changed that to, if I actually do the tangent to a point and do the gradient, therefore, I would know the speed, the instantaneous speed at that point. Does that make sense? So the green, which I know doesn't make, if you're not writing in green, so you have to find some other way of noting it, the green triangle would be the average speed, right? But the tangent, okay, will be the instantaneous speed.
Do you find the gradient of the tangent? So how do you draw tangent if you don't know? Like, I
But
think
we
you
don't
have
draw
to
tangents
explain.
now, do we? We find the differential of the equation, and
So why was it going to draw the tangent in the first place?
it's just explaining it. Because you might have to draw a graph, draw a tangent, and estimate. Remember, we've done that before.
I don't know how they do to, or what they
Because it will say by drawing a tangent, or it will say use the graph to estimate the speed of, or so the difference is if you wanted to know the average speed between 2 points, you would do the rise over run thing. But if I was asked to estimate the speed at 10 seconds, I would do the tangent at that point and then work out the gradient of it. Yeah. So it's the difference between the average speed between 2 points and the instantaneous speed. Now, if I'm given the function, I just have to work out the differential equation. Right? Just like you've been doing all along, exactly the same rules. It's just how we're interpreting it now. Right? So if we go through a couple more, it might make some sense. So the ones in the book. So it says h of t. Now you'll see a lot of these have t because it's with time. Rates of change are all going to be with time. So this will be height above ground. Okay? So that could be of anything. It could be a rocket launched or whatever. But quite often what they do is they set up a problem where, do you know a Ferris wheel? Yeah? At a fairground. And what they do is they set up a function. They give you a function where if you're here, then the height above ground is h. I'll call it capital H because that's what we've got. And as time progresses, you obviously go round the Ferris wheel and you get higher. Now as we keep going round, you then get lower. And you go back and you keep going round. Now notice how I'm not looking at the horizontal distance, I'm only looking at the height. So the height will go up and down. Does anyone know what the shape of that curve will be?
Sine.
Yeah, you've done that. Yeah, you've seen that. That will end up being a sine curve or a cosine curve. Yeah, cyclic function. Now we've got height measured at different times. So that might be time 1. This might be time 2. This might be time 3, and so on. We're measuring at different times. What would dh dt be? Go on. So the rate of change of height with respect to time. So what would that be with a Ferris wheel? If I increased the rate of change of height what would that tell me about the wheel?
The speed that it's
Well, when you say speed, you mean how fast it's turning, yeah? Right? And they call it in the book the rate of ascent. Now, this one will have, obviously, as it's going up that way, the rate of change of height will be positive. As we come down that way, the rate of change of height will be negative. So we'll be able to see that, and it will go positive, negative, and so on, as it keeps going around. But as we said, if the gradient function, if the rate of change function is larger, if it's a higher value, it just means the wheel's turning faster, yeah? So it's about how we interpret these things. The final one that they've got in the book, me.
I don't understand.
Go on.
Why are you worried about speed? Why, if they said the rate of change is higher than any speed?
It's how quickly I'm turning the wheel. So for instance, you might turn the wheel and it's going really slowly. So my height, as you know, if I'm in this cabin here, I would go up really, really slowly, yeah? I'd be getting higher, but really slowly. But if I was in like a fairground one, more of a thrill ride, they would increase the rotational speed so that I would get higher quicker and then come down quicker and then higher quicker and so on, yeah? So this here tells me how quickly my height is changing with time. And the higher that number, the higher the rate of change, the faster the wheel must be turning.
Which number?
So if I work out a value for dH dt, so for instance, if I said to you dH dt was 7, yeah? Or if I said dH dt is 15, this one would tell me that the wheel is now turning faster because the rate of change of height is faster than it was before. I'm now going up 15 meters every second, whereas before I was only going up 7 meters every second. Does that make sense? Yeah. So the higher. Did you all get that, by the way? So these values, let's say I just made up values. I have literally just made up values. So what does it mean? Let's say I'm going to change it to centimeters just because it's. So this would be height is measured in centimeters. Time, let's measure in seconds. So this would be centimeters over seconds or centimeters per second. So that means that my height is changing 15 centimeters every second. So I'm going up, right? When it becomes negative, I know I'm coming down. So that's one thing I guess we should say. Positive means we're going up, but a negative value means the wheel is turning so that I'm coming down. Now, if dH dt, so dH in centimeters, dt in seconds, was 7 centimeters per second, what that means is I'm only going up 7 centimeters every second. So I must be turning slower. Yeah?
Do we ever have to figure out at what point the distance will become like negative?
Yes, exactly. So these are the kind of things you're going to get asked, aren't they? At what point in time do you reach the top of the Ferris wheel? So when does the dH dt, you know, or sorry, when is, so that's when speed would be, well, height would be going from positive to negative. It would also be when is the wheel stopped, stationary, yeah, that kind of thing. Just to go back to this one then, what are the units? Let's just check. So distance would be again in, let's say, meters. Time would be in seconds, let's say, or minutes or whatever. So the rate of change, also known as speed, would be meters over second, meters per second. Okay, but this time it would be a straight line or speed or whatever, yeah? Now the fact that ds dt is going to change because we have a curve means the speed is changing all the time. So hence we might be getting faster or not. Just to maybe check understanding then. Right, before I go on to the final one. Alright. If I have a function which is s of t, so that's distance, okay, ds dt we've said is speed, yeah, so basically s is in meters, this would be meters per second, right? What if I were to differentiate again? What if I were to differentiate the gradient function? And this is called, by the way, trying to get which way around. It's d2s over dt squared. This is what we call the second differential. Alright? So we've got the second differential. Alright? And this is an important one because this would be, if I were to differentiate speed, what would I be getting? I'd be getting the rate of change of speed. What is that called? Acceleration.
Oh, yeah.
So that's a common one, especially in physics. I differentiate distance, I get speed. I differentiate speed, I get the acceleration. So my second differential. Now, you know, there are other times when we would maybe want to consider the second differential. Okay? But just to show, distance, speed, acceleration, they're all linked. So I can take the distance function, differentiate it, get speed, differentiate again, and get acceleration. Alright? So, for example, if I said speed is 5x squared plus 2x plus 6, that would be my distance function. That'd be like a projectile motion, actually, a quadratic. In fact, it doesn't make sense. Anyway, it doesn't matter. What would be my speed function? 10x plus 2. Now the fact that I've got 10x plus 2 means that my speed is still changing. Because as x changes, speed changes, yeah? What would be the acceleration?
Yep.
10. So I differentiate 10x plus 2, I just get 10. What does that tell me about the acceleration?
It's constant.
Constant. So we have a constant acceleration
Oh, boy.
because it's just a number. Acceleration. So what would my units be again? So if my distance is in meters, my speed would be in meters per second. My acceleration would be in meters per second squared.
So I didn't quite understand how you mean it's constant.
Because it's a number, it's always 10. It means my acceleration is always 10 meters per second every second. That's how much quicker I'm getting.
So what would be something like, what's an example of it?
It's just always
So if, for instance, I ended up,
Just a number?
it's not probably, but it might be that acceleration also changes with time. So for instance, all right, if I were to take a space rocket, yeah, you would have maximum acceleration at the beginning, yeah? right? And you want that massive lift to clear the ground. But you're still accelerating, you're still getting faster, but as you get higher, you might cut it a little bit so you're not getting faster as quickly. So you might cut the acceleration. So what's the... Well, no, you wouldn't be decelerating. You'd just be accelerating less. So I'd still be getting faster, but not at the same rate. Now, do you know what acceleration feels like? I'm sure you've been on your scooter, as I've seen you all out on the roads. When you accelerate hard, what does it feel like on the bike? You get pulled back, no?
Yeah.
I know you've got little 50cc's and things like that. But when I had my 600cc motorbike and I accelerated hard, I would be thrown back and I'd be holding on. All right?
Where?
Switzerland, I don't
Yeah.
know. You can't, you're not allowed, it's illegal. Everywhere else in the world, you'll enjoy it much more. The way you drive, you'll kill yourself, but if you accelerate hard, you get thrown back. If you don't accelerate so hard, you don't get thrown back as much, yeah? So that is the effect of acceleration, and that can change. So in a rocket, you get thrown back in your seat, but then if you start to accelerate less, you might find I can sit forward. I'm still accelerating, I'm still getting faster, but not at the same rate. Now, this would be more example of something like if I drop an object from the top of a building, it will accelerate. Do you know to what extent? Acceleration due to gravity. Yeah. What's the amount of gravitational pull?
10.
10. Is it always 10? Yeah. So you will accelerate at the force of gravity, yeah? Now, is there ever going to be a point at which you stop accelerating?
Yes.
Yes, because you reach terminal velocity.
Yes, that's what it's called.
So your acceleration will gradually slow down to 0. You will no longer accelerate anymore. Hence, we will not have a constant acceleration. All right? Does that make sense? Okay, let's look at the final ones, which is they're saying dc dt. So they are saying if c with t, okay, ct, a function of c, is the capacity of someone's lungs over time.
Wait,
Okay.
doing capacity?
So the capacity of someone's lungs. So what happens? Does the capacity of your lungs change?
Yes.
How?
In and out.
In and out. So as you breathe out, your lungs are contracting, yeah, to force carbon dioxide out. So the capacity of your lungs is smaller. That's how it does it. It compresses, forces everything out. So, and then when you breathe in, I remember my physics teacher once telling me there was no such thing as sucking in. Right? You're actually expanding your lungs, creating a vacuum, and that pulls air in. So you expand your lungs, you create a higher capacity, air has to come in to fill that. So as you breathe in and out, the capacity of your lungs change. So we can have a function that measures that. All right? So dc dt would be the rate of change of the capacity. So what would these two values, so if I said dc dt equals 2, or I said dc dt equals 8. So what are the units, do we think? So capacity would be measured in, well, it would maybe centimetres, centimetres, just centimetres? Centimetres cubed, because it's a volume, right? And time is in seconds, all right? So we've got the rate of change of volume. So we are saying that volume is changing at 2 centimetres cubed per second. We might also, by the way, DC might be done in millilitres or litres or whatever the way we do capacity. Or this would be centimetres cubed per second. Now if I said to you, and which is quite often in these type of questions, interpret that for me.
That
In terms of breathing, what does it mean?
Yeah.
So if I increase the rate of change of capacity, what does that mean?
You breathe in quicker.
Breathing quicker.
Oh.
Is there going to be a negative in here as well?
no. I mean, yeah.
Yeah.
Yeah. When you breathe
Because it's like the Ferris wheel goes up and down. You're breathing in, out. You don't just keep breathing in, do you? And expand and expand and expand. All right. But I would have how. So if I were to measure, for instance, on a machine, the rate of change of capacity of your lungs, I'd be looking at how fast you're breathing in and out. Yeah. Okay. Right. Well, let's have a look at a question. Just one ought to do it. I think we've done quite a lot of it. So it says the volume of hot air in a hot air balloon is measured at 2t cubed minus 3t squared plus 10t plus 2. And that's in meters cubed. Okay? So there are my units. Find the initial volume. So they always like to do that. The initial volume. So what you are expected to know there is the initial volume is when T equals 0. Before any time has passed. So that's the important thing there. When T equals 0. Change that colour. It's a bit too much.
Yeah.
So when T equals 0, initial volume, initial means when T is 0. So there's a long way and a quick way. We either go V equals 2 times 0 cubed minus 3, 0 squared, plus 10 times 0 plus 2, and we work it all out, which is then 0 minus 0 plus 0 plus 2. Or we know that the plus bit is what it's going to be. Alright? So it's always this number on the end, the plus 2. Alright? So we ought to, again, in questions like this, there'll be unit penalties. So the volume initially will be 2 meters cubed. So unless it specifies it in the answer slot, make sure you write that. So then it says, what about the volume? Okay. The volume when T is 8 minutes. So again, they kind of just repeat this to check that you do. If you did just take the plus 2 at the end, they check. All right, well, we'll see then. So do you know how to do 2 times 8 cubed minus 3 times 8 squared plus 10 times 8 plus 2? Okay. And that ends up as, because it's in the book, so I'm not doing it in my head, 914, but again we need to say meters cubed. Okay. Then, finally, we are being asked to find the rate of change of the volume, okay, when T equals 4. Or actually it says rate of, it actually says increase. So if we know it's an increase at that point, then we know that the what we're going to do, we're going to do dV dt, the rate of change of volume, and we know it's going to be, if it's an increase, that means it's going to be a positive value. So that's what we ought to check. So, what is dV dt? Well, if I imagine that's an x, so 3 times 2 is 6. We've got 6x squared minus 6x plus 10. Alright? It's in your book if you're not getting what I'm doing there with numbers. So. Alright? And then what do we do? So we want when t equals 4, so we have dV dt, so that's 6 times 4 squared minus 6 times 4 plus 10. Okay? So we end up with 82. Right? And the units are meters cubed per second. Are you all happy, by the way, with the physics thing of doing meters cubed seconds to the minus 1? You recognise that? Because that's like doing 1 over x is the same thing as x to the minus 1. So if it's 1 over seconds, so when you write meters per second, it's like doing meters cubed times 1 over seconds. So the 1 over seconds is seconds to the minus 1, so it's a different way of writing it, but it's the same thing. We've kind of got 2 minutes till lunch, 3 minutes till lunch. Clock's slow, I told you.
Oh, it is?
Yeah. Okay, now it's not in the book, but what if I said to you, how much volume is in the balloon when it's at that rate of change? What would you do? So how big is the balloon when it's at 82 meters cubed per second?
If it's at 82 meters cubed per second, then that means the time is 4, right?
Yeah, so we know already. Time is 4, we were given that in the question. So we would just do, we don't need to rearrange it, we just go back to V, right? We put V, we work out what V was when t equals 4. It's just simple, there's nothing tricky about it. It's like, no rearranging. I know that it's 2t cubed minus 3t squared plus 10t plus 2, back to the initial one, and I just put t as 4 in this time. It's just another way of asking the same question. Now I could ask it in even another way and say, at what time is volume 500? At what time is the rate of change 100 meters cubed per second? That kind of thing. And that's what we need to look at in the next thing, right? So this is what's going to happen now. We're going to have one lesson where you can go through the rest of the stuff, questions in your book on rates of change. One more. And then I'm going to get on with other things that we need to finish off. Okay? So do whatever you need to do for homework to be prepared for this finishing. Because you are having your test on this, we'll say first week back, didn't we? Alright?
When did you say I went for the first work? That's the last one.
Oh, I said it had to be, if you want to check, it had to be Friday
This Friday?
this week.
This week?
Yes.
Well, deadline, no. I am not doing anything over Christmas. If you want me to check it, you give it me on Friday. I will have a quick skim through. That's it, this stage. Well, I'm not supposed to give that, but I will for everyone, because a lot of people didn't do what you did and handed it in first time. So I'm giving a second chance. Okay, but it will only be a quick skim through. So for you, it would be great because you've got a second piece of feedback. So, yeah, but it must be Friday, 4 p.m. Friday. I just delete any email that comes in. I'm not even going to consider it. It will be final deadline. Okay. All right.
Final deadline for feedback.
Yes.